Well, good afternoon, and why don't we get started? As usual, we'll start with a few reminders. Homework was due for calculations part 1 and sources on Monday. A few of you asked for an extension that was granted till tonight at 11:59 p.m. If for some reason you still need an extension or there's an issue, just email me and I'm happy to work with you on that. On Friday, we will have a special guest speaker. Dr. Lupita Montagna is from the University of Colorado in Boulder. She is a specialist in air quality and has done extensive work on the confluence of COVID and air quality, in particular in both the Navajo and Latinx communities out in the Boulder area. So it's really thrilled that we can have her come and speak. She'll be addressing some issues also in terms of environmental justice that I think are really beneficial to consider as we talk about air quality. Next Monday, there is another homework due, and it is on health effects, indoor air quality, and OSHA regulations. What I want to do today is a little different. I'm not going to do a new lecture, so we're not going to cover new material. I have a number of problems that what I want you to do is to work through these in base groups and breakout groups. So what I've done is I've created a series of problems. We're going to work through that. This initial one, what I want you to do in the base group is to read over this, draw a diagram, and then answer the question. Okay. What is the steady state concentration of carbon monoxide entering the duct? So it leaves the reactor, enters the duct, and also at 1 meter distance from the reactor effluent outlet. Okay, I'll give people a little more time to get back into the main group. Okay, so probably could have given you a little bit more time here, but hopefully gave you a little bit of time just to think about this problem. So this is setting up a problem. So let's just switch to the next slide. So let's think about this. So we have a reactor, we have a flow in, and we have a flow out. We're told that there's multiple contaminants entering the reactor, but the one that we're concerned about is carbon monoxide. And we are told that the carbon monoxide is conservative, so that means that K is equal to 0. We are told that the influent concentration is 40 milligrams per cubic meter. We have a completely mixed reactor. You're told that the volume is equal to 50 cubic meters, and you're asked for the concentration leaving. A number of you wrote the basic equation that the change in mass with respect to time is equal to C sub A IV plus S minus C out IB minus K C out. So if this is the situation, this I times V is Q. And the C sub A is equivalent to the C naught. The S term is equal to what? 0. Excellent. We have no source within the reactor. And since K is 0, the last term is also 0. So what is the concentration leaving at this point right here, leaving the reactor?
The same as the inflow.
Yeah, exactly. It's the same as the inflow. And if we have a pipe, a duct, and it's 1 meter, what is the concentration leaving that duct? It's still 40 milligrams per cubic meter. It's still non-reactive. It's still a conservative pollutant, so we can then state that it's 40 milligrams per cubic meter. So the reason for this problem was just to try and get you to review some of these terminologies to set up the problem so that we can move forward. Okay. The next problem's more complicated. So what I will do is I'm going to give you 10 minutes for this one, providing I can do the base group, set the base groups up properly, or the breakout groups. So I just have to change this here. So we'll set it to 10 minutes. Okay. I will open all the rooms again. So you should be in the same group, same Google spreadsheet. So if you just move down, you'll see that the next problem is there. So what I want you to do is to work through the next problem. I'm less concerned with the answer. I'm more interested in you drawing a diagram, thinking about the system boundary, and setting up the problem. I know you can do the algebra. That's not the goal right now. The goal is to really set up the problem. So I'll give you 10 minutes to do this. So let's work through this problem here. So what do we have? We have a situation here where we have cabin. We have infiltration. We have C sub A. We have C out. We have the exfiltration. Well, the I equals the infiltration equals exfiltration. We have a wood burning stove, and that is releasing benzene. And you're told that you're burning 2 kilograms of wood per hour. We're going to assume that that use of wood is just constant. The volume is 75 square meters by 2.2 meters. I is equal to 0.75 air changes per hour, so that's inverse hours. We're told that the ambient concentration entering the cabin is 0. And we're told that benzene decays at a rate of 4 times 10 to the minus 3 inverse hours. And you're also told that benzene is generated by the burning wood at 1.94 grams per kilogram of wood burned. We burn 2 kilograms per hour. So we produce 3.88 grams of benzene per hour. So that's the source term. And a number of you wrote the equation correctly. So the change in mass with respect to time, and volume is constant, so we can pull volume out of the differential. And that is equal to the mass in plus the source term minus the mass out minus the mass reacted. And mass in is C sub A times I times V plus the source term minus C out IV minus K C out V. I've made a number of assumptions here. The K is inverse time. Wherever you have inverse time, you should assume that the chemical you're considering is decaying according to first order kinetics. So first order kinetics simply say, in this case, it would be the rate of change in benzene, the rate of reaction of benzene is equal to the rate constant times the concentration of benzene. So this is first order kinetics. So that's what we've assumed and used right here. We've made the assumption that the concentration in the reactor or in the cabin is equal to the concentration leaving the cabin. So we can assume, what have we now assumed in this situation? So we've made the assumption that C in the cabin at any point in the cabin is equal to C leaving the cabin. So what assumption have we made?
Well mixed.
That it's well mixed. Exactly. So we'll put a big fan up here to dim. Now, we don't necessarily have steady state conditions initially. We are producing benzene at a steady rate, but we can integrate this expression here. And as I mentioned the other day, if we integrate this expression, it yields this equation. So you will not have to do the integration. If you don't have steady state, this is the most general form of the equation that you will use. So at this point, it's just a substitution. So if we substitute, and we're looking initially at 1 hour. So if we substitute various parameters that we have into this equation here for 1 hour, what we will find is that the concentration of benzene is 16.5 milligrams per cubic meter. So I haven't written out the substitution, but it's just simply substituting. This is what we will use for S. Remember, S should always be in mass per time. So the answer that I get is going to be in grams, because notice here, S is in grams. Make sure your units are consistent. If you had an ambient concentration, make sure that the concentration units for S and your ambient concentration are the same, along with your C naught. All of those, if they're all in milligrams, they all need to be in milligrams. If they're all in grams, they need to be grams. So this would be the concentration after 1 hour. I've plotted the data here. So 1 hour is right around here. So this is 1 hour. What this plot shows is that students arrive right here. They get the fire burning right after they arrive. Concentration of benzene increases over time. And then once that concentration is constant, what conditions are now prevalent?
Steady state.
Steady state. So we're at steady state here. So it reaches steady state after roughly about 5 hours. System is reaching steady state and the concentration approaches a maximum, approaches about 31 milligrams per cubic meter. And just to kind of give you a comparison, we will talk, when we talk about OSHA regulations, we will talk about, I mentioned permissible exposure limits. I used that term the other day. So a 8-hour, what we call time-weighted average, so it's an average over 8 hours in an occupational setting, is 1 part per million. This 31 is equivalent to 9.7 parts per million. So what does that tell you about that concentration?
Higher than the permissible limits.
Exactly. It's higher than the permissible limit. We'll talk about permissible limits, but that's set for a worker, good health. That tells you that there is significant issues with that concentration. What would you do as the engineer?
Ventilate.
What?
Ventilate.
Ventilate,
Or-
exactly. You could either reduce the amount of wood that you're burning, but then you may be cold. So open those windows, get some ventilation in. You'd want to reduce that concentration. We're not going to have time to go through all of these problems. I thought we'd get through more. But this is another situation. Here we have, this is set up as a bar. We have a number of people smoking. Each cigarette is emitting formaldehyde. Formaldehyde has a rate constant. You've got an infiltration rate. Similar situation. And again, I've asked you to determine the formaldehyde concentration in the bar at 10 p.m. I'm not going to go through the whole problem. It's very, very similar to the previous one. The major issue here, looking back, is basically you're just looking at this information where the complication comes in, because half the patrons are smoking 2 cigarettes per hour. Quarter of them are smoking 1, and the other quarter are smoking none. So this gives you this 2 pieces of information give you then the amount of formaldehyde that is being emitted in milligrams per hour. That's your source term. Everything else is identical. And you see you have a similar plot here. And again, what you see is steady state conditions. In this case, after about, actually, it looks more like 8 hours. Typically, it's fairly common, okay? Depends on your infiltration rate, how long it takes to reach steady state. But again, we've reached steady state here, and the concentration is increasing with time. What I've done here is I've plotted this in with different infiltration rates. So you can see if we start, problem was stated with an infiltration rate of 0.5 inverse hours. If we double that, you see that the concentration at steady state decreases significantly. If we half the infiltration rate, you see that the concentration increases significantly. The other thing you can see is it reaches steady state after about 6, let's say 6 hours, 8 hours, but let's say 6. If we increase the infiltration rate, so we double it, it's reaching steady state after about 3 hours. If we half the infiltration rate, we're just starting to reach steady state after 10 hours. So it's actually going to take closer to 12 hours to reach steady state. So at all other conditions constant, the infiltration rate will play a significant role, impact on the time that it takes to reach steady state. I'm just going to, and then actually let's look here. So what happens here is everyone goes home. So there's no more smokers. And you can see that now S is equal to 0. And the concentration, because C sub A is equal to 0, the concentration will decrease until it reaches 0. And it takes longer, which you'd expect, to reach 0 with the lowest infiltration rate. So the greater we ventilate, the faster that concentration will reach 0. Any questions about this? Hopefully going over this was helpful. The next set of problems are very similar to what we've done today. And I've tried to set up these problems to help with the homework. I'm happy to answer any questions.